All right. Well, I'll start introducing Manu, and because I want to really have as much time as possible for him to talk about as much of the wonderful things he's doing as he can. So it's really a pleasure to introduce Manu to our first virtual and hopefully not for too much longer virtual Epicenter seminar series. Um, we owe Manu a dinner and some other in-person events, which it's now public, so you can hold us to it, Manu. But it's really our pleasure to do so. And it's just fabulous to have you presenting here. So I've known Manu for some years, as have other people in our group. And every time I hear him talk about something, I'm always surprised, because not only is it incredibly interesting, but it often has, something completely distinct from what he's done before. So the breadth of what Manu works on is just something that I'm sure keeps him interested in what he does every day, and always keeps me wanting more. So just for the formal introduction, Manu is an associate professor in bioengineering at Stanford. Where he's been working for a few years. He's an HHMI faculty fellow, of Chan Zuckerberg BioHub investigator, and has numerous awards, including a MacArthur Genius Award, National Geographic Award, award from Wired, from Rotary. And one of the interesting things I found out on your CV is you're a member of Plankton Planet, which is something that sounds like would be fun to check out at some point. And author of hundreds of articles. And in addition to having such a breadth of work stemming from really fundamental studies of life and how we've evolved, the first talk of which I finally heard a few weeks ago, which was just fascinating, about organisms I never knew existed, to really practical engineering solutions. One of the best things about Manu is that he is just a really incredibly warm, engaging, and nice person to meet, which unfortunately you'll only get the Zoom flavor today. But if you ever have the opportunity to meet Manu in person for lunch or just for a quick chat, he's so accessible, despite how brilliant he is, that he's really just a special person. So with that, I'll let you talk about some of the wonderful things you're working on, Manu, and thank you again for giving our seminar today.
So thank you for having me, and such a warm invitation. I really wish we could do this together, because I'm here to learn. I think one of the things that I often enjoy is with a broad range of communities and things that I work in, I have mostly far more to learn than to share. Uh, I'll kind of set the stage of the conversation in some sense, but my hope is that this really becomes a mutual exercise for everybody who's engaging. Um, it's always hard for me to choose what I'll end up talking about. So what I'm going to do is juggle a little bit back and forth. And since you just mentioned uh, briefly the kind of the breadth of things that we do, maybe I'm going to show one or two movies as kind of just to tell you what inspires me and what gets me started. And majority of this talk will be really about what I call frugal science, and I'll explain what I mean by that. But part of my framework of how I think is also really captured in this book. It's a children's book that I absolutely love. If some of you either have children or just have forgotten your childhood, go get this book. It's only a few pages, but I think sometimes, often enough, we think about applied and basic in such dramatically different ways. We forget that we connected at the hip. That there is this circular argument about curiosity, and many tools that we build and share come from curiosity, and then they go back to becoming maybe valuable to society per se as a tool. And then sometimes you're trying to build something uh, really esoteric, and it has really other implications. So I think for me, this part is very important. The other reason of me being a little bit of what scatterbrain is because life on this planet is a scatterbrain. So this is my second plug for a book. None of these books are written by me, so I feel comfortable making a plug for it. This is my second favorite book in biology. It's called The Golden Book of Biology. It's also very difficult to get access to because Only limited copies were printed. This is a very famous illustrator, Charlie Harper. What I love about this picture that you see in this book is he's drawn the tree of life with organisms to be of the same size. And so, because I know many of you think about infectious diseases, look at the bear and the giardia at same scale. And what he's trying to communicate and again, I don't need to convince all of you, but think about human population and its impact, and think about a tiny little minuscule coronavirus. They should be drawn at scale. And at the same scale, small things can have dramatic impact. And I think much of the work that I often think about these small scales because small organisms are often hidden, but they have remarkable capacity to teach us. And I often feel in the context of ecology, which is what led me to some of the work in surveillance, is this notion that there is 9 to 10 million species for us to learn from. We have a tremendous amount to learn from the parasites themselves, which keeps me intrigued in the biology of the parasites as well. And this juxtaposition of basic biology and applied science is quite well illustrated in just the tree of life itself. So this is the second book if you've never had the chance to look at it. And maybe I'll just show you one or two fun videos, and then we will jump into really kind of the meat of this talk. But I do want to share this other side of me, which is, again, sometimes people think about, we make tools and we make affordable tools as a lab. And often people think that these affordable tools are valuable for people far away who might not have kinds of resources. And the answer could be farther from the truth. So what you're about to see, for example, is a phenomena that I discovered just mucking around with a foldscope in a swamp. And it actually turned out to be quite a full question in biology. So I'm just going to play this video for a second, and you will watch one cell eat another cell. And we'll just let this play by itself. What you're looking at is a single cell that is literally engulfing, and the video is a little bit choppy. Let me zoom out of this, and I'll just play this one more time. This is sort of like a, say, whatever a cheetah captures. And this is all happening in real time. And of course, just this one set of observations has actually led us to understand remarkable aspects about how plastic a single cell can be. And so you can see the neck has opened up, but there is no neck. This is not a multicellular organism. It's a single cell. I am anthropomorphizing it by calling the word head and neck. But again, we really discovered this phenomena by just being in the mud, looking with a foldscope and finding something. And that has led us to really understand something very basic. This happens to be, from a deformability perspective, the most agile and deformable cell that we are aware of. And similarly, we discovered another cell which has the world record of being the fastest cell. And so what I mean by fast is to observe this cell, but I want you to pay attention to the time scale here up on top. And I'll just play this video. This is a high-speed video, and within 5 milliseconds. So, you know, when you blink your eye, that's around 16, 20 milliseconds. In 5 milliseconds, the cell just contracted. And this happens to be one of the fastest movements in terms of cell biology. And of course, look at the scale bar. Talking about a cell that you could see by naked eye. And when you think about sort of the origin of muscles and other sets of things, in the diversity of life lies these kinds of phenomena that just have not either been observed or studied, for example. And it pushes our bounds of thinking a lot about what is the importance when scientific tools are more broadly accessible. How many more discoveries could be made in life science, these types of tools? And again, these are two examples of things that I literally discovered using a foldscope. And of course, when we brought them to the lab, we applied all kinds of tools to understand these things. But on the other hand, without that tool in our hands, we would not have actually experienced these things or actually discovered whether something like this could have ever even existed.
So Manu, just channeling
Yes.
Bill Burkholder, a fold scope, for those who don't know, is a low-cost microscope that you may or may not talk about later.
That's correct. Actually, I will briefly mention it, but not too much. Yes. So let me begin with that framework, and I think it will come back a couple of times in this context. The talk that I really want to share with you, a broader idea, is something that I've been thinking about for many years, and I know many of you are passionate about this, which is, as scientists, what defines the role of science in our society? What does it mean for many of us as tool makers to share? What does it even mean to solve problems in society? And I think as scientists, I could not tell you, COVID was just such a dramatic example of this happening, that of course all of us are thinking we are solving problems, but what does it truly mean to solve problems, and how granular do we need, how much you really have to wrap your arms and make sure something happens that you want it to happen? So I think there are several philosophical questions that we've been thinking about for the last couple of years, but all of them are driven by tools. So I'll share a few examples of tools we've been building. But the hardest part that I often find in these, which is really the discussion that I would love to have, is what does it mean to share a tool with a community? What does it mean to nurture a community and for it to actually be useful at a level that you're passionate about? So this is a picture of a rural village in India where a teacher sent me this photograph. And I think if you could hear, if you were in that room, you would have imagined these kids would just be, there would be this sounds that are coming along in the excitement. But literally notice that there's only just one fold scope in this entire picture, which is at the front. And I mean, this also picture makes me sad because it really teaches me that, okay, we have reached the level in which we could make technologies accessible to everyone. And I think this is really true for much of everything that I'll tell you about is really in its nascent stage of what we are trying to truly do. Okay, so the term that I often use in frugal science kind of also gets confused sometimes with other terms. And what I mean by it is quite precise, which is how do you bring scientific tools and access to scientific knowledge at an order of magnitude cost reduction without not a significant hit in performance. Of course, we believe that there is this sense of a coordination between these performance and cost, but it doesn't, sometimes when you think hard about it, you can actually not just follow the slope of one, but you can build things that would cost orders of magnitude less, but the performance would not take a dramatic hit. Performance should really not be measured by what is absolute, but what is dependent on the context. So this is what I really mean by frugal science. And the way that I would frame this, and I think this is really true for all of you when you think about this, that of course we have a picture of UCSF, but this is also a hospital or a healthcare center. This is a picture that I took in Ghana of a clinic that gets organized once a week. And people would show up at this clinic. Or, of course, the doctor would come once a week in a van. And I think this is not far away from many places that you all work. There was a beautiful study that really looked at, what is the distribution of hospitals all across Africa, for example. And one of the factors that was highlighted is just the fact that distance is a huge challenge in people getting access to healthcare. And this is the picture on the right is a photograph from one of sites in Madagascar, where it's very common to walk between 10 to 12 hours to reach a field site. And I'll talk quite a lot about malaria. And one of the things that you all know is malaria hides in places around the world where access to roads and infrastructure is fairly limited. While I started my lab thinking a lot about health, and it kept coming back that education, and without thinking about education, we could not address health. This is another picture that I took in the field. And again, you can already tell that many times the way we think about education is almost to an extent that just having a roof does not make a school. And that made us think quite literally about the value of education and building that as part of all our programs that we work in. And again, this is not new to anybody that works in global health, but science education is deeply connected with health. If you cannot hospital, what would be the point of building these sets of facilities if just there is no buy-in from the community? Uh, and then the last one, which again happened accidentally as we spent some time in the field, but again is so crucial for epidemiology per se, is just what is happening in the environment. And this leads us to be thinking about tools that should be applied to ecological surveillance. So the three sets of often think about is health, environment, and education, and building a broad range of tools that are applicable in all of these three domains. Because to me, these three domains are not disconnected. We could tackle a few problems, but if we are building and designing general tools, I would like them to be applicable in all of these areas. And of course, the environmental and ecological pollution is definitely one part of it, primarily some of the detrimental effects that we see in an ecological context are actually related to this. Uh, so one of the things that, and I'll briefly mention COVID per se, is an example that I find in all of these challenges, and especially thinking about health challenges that are always quite daunting, is this notion that sometimes in a context of crisis, ideas that dramatically shift and change what is possible. So this is the story of invention of bicycles. I don't know if how many of you know how bicycles were actually invented. It was invented only because there was a volcanic eruption in the 1815 that led to a gigantic cloud across of Europe, which essentially led to a famine that led to the horses dying and people lost their key transport. And this is when Carl von Drais came up with this notion of a mechanical horse. And although the famine returned and everything came back to normal in Europe, bicycle remained. And of course, you can see how powerful an idea it is. So from a context of crisis, I often think about when we are talking about global health and these pandemics, these are also the moments that we could bring something to fruition that would have never existed without this forcing function. So, although it's been a really difficult year for all of us, I really do feel that this could be the golden age of global health. If we took and really took to mark of what we learned from last year, it could truly change the paradigm of how to think about health delivery in some sense. So I'm always looking for what is the bicycle in some way. Okay, so let me for these projects, and then I'll give you a few examples of the framework that we use, and then I'll dive into a few concrete examples. So firstly, for all the sets of problems that I described, there is one thing in common, which is they are unfolding across the planet. And often enough, the second thing that's in common is the shortage of communities and especially scientists that could actually engage in these sets of problems. So for all the that we build, we think about these two axes is how do we make sure that it's affordable? And secondly, how do we make sure that we could really build an interface between amateur scientists or communities? And when I think of amateur scientists, I put health worker in that category. A community health worker that has a high school degree or a seventh grade school education, to me, is an amateur scientist because they're engaging in the process, the formal education per se. And actually, in my mind, that is also the world's largest citizen science program because they really support much of the global health community at large. And the thing that I'm interested in is understanding how do we make tools that are not just applicable and usable by scientists, but are also usable by community members that are integral to the entire process of delivering this care. And one example that I find valuable is from a historic perspective. I don't know if some of you recognize what this object is. Um, for some of you, appropriately aged, you could tell what this object is.
Is it Sputnik?
It is Sputnik, that's correct. This was when the Russians launched Sputnik. Something very interesting happened. The US had no capacity or capability to track and whether there truly was a thing that was flying in space. I mean, the Russians could have just made it as a hoax, for example. And at that time, an astronomer named Fred Whipple realized the scale of this problem, and he delivered on what is called Operation Moonwatch, which was the world's largest amateur citizen science program in the world. At that time, thousands of astronomers, they shipped these tiny telescopes around the world, trained people, taught them how to track these satellites or artificial satellites, and use this data. So this is not just people just collecting and taking, observing for fun. They were collecting real scientific data. And for the next 60 years, this network was the most comprehensive network for every single satellite that was launched. To an extent where if you look in this sentence right here, it says Mrs. Lloyd Eisenhower, housewife volunteer sought Sputnik 2. And majority of the satellites when they were launched were first tracked by these individuals, then reported back to the central facility, especially the defense arm of the United States. And then the army was notified that the Russians had actually launched something new. So 7 or Sputnik 5, I think, was identified primarily based on one of these amateur scientists. And when I think about a pandemic and I think about all the global changes that are happening, we need to rethink about what does it mean to mean planetary scale measurements, and what does it mean for communities to be empowered to really be the watchdogs of what will happen on our planet. And again, I'm not saying I have an answer to this, but just what we have currently from a surveillance perspective is good enough. Okay, so what we will mostly talk about is healthcare workers and tools that healthcare workers could use. And I very strongly feel that this is really the community that we need to empower. What are the appropriate set of tools that go into a backpack of a young person that's, say, 22 years old, that is putting their life on the line, going into a village that has Ebola, or, for example, going into district, for example, and delivering healthcare services. So I don't want to make any distinction between developed versus developing countries. The distinction is haves and have-nots. And what would you need? What are the kinds of tools that are actually needed to deliver these kinds of services? And of course, this is a big challenge because, of course, for every specific type of a problem, there are different kinds of tools. So in terms of the number of tools, there is a large number of things we have worked on in the past. I'm not going to touch all of them. Many of them are published, so I'm assuming some of you could find some of these tools and ideas. I'll just choose one or two and dive in a little bit deeper to tell you a little bit about the history of how they have evolved and where we are taking them. But if you want to find out more information about any of these sets of tools, at least we have worked on, especially in the context of surveillance, parasitology, more fundamental parasitology, or diagnostics, you can just, look up some of these papers, for example, or ask questions. So let's choose a few examples. And then before we start, I think another important philosophical comment that I want to make is a lesson that I learned in Uganda, and actually that I have to thank the UCSF Malaria Initiative for. They were kind enough to invite me to visit Tororo and spend a couple at the field site. And I don't know, Brian, if you can identify this individual in this picture G. He was the head of the pathology of the Tororo hospital. He has a foldscope in his hand, so it's hard to see. I very distinctly remember meeting him in 2013. And one of the fascinating things about that was he said something. We had just developed a version of foldscope, and he said, "Come back to me when you can do diagnostics under a tree." And I didn't understand what he was talking about. What do you mean diagnostics? And he really explained it. He said, look, I've been training people for the last 40 years, and I really feel very strongly that the tools that we have are just not sufficient for the challenge that we have. And this is why I kind of, I'm not, of course, the contributions we make are focused on technology, but that really struck with me. This idea that he was thinking about this notion that these tools should not be dependent on any infrastructure, because you really require, and I'll talk a little bit about a COVID test that we've been developing that has really been shaped by this word about diagnostics under a tree. So anyway, it was a remarkable moment personally for me, because it led me to be thinking about really stripping away all the complexity. And sometimes as scientists, it is hard to do because we all love to quote the performance, and to add to the performance, you always need to add bells and whistles. But it's been quite a valuable lesson, at least that I learned along the way. Okay, so maybe just a brief detour on the context of COVID. This has been the timeline of products that we have released for COVID, starting from March, when at least I got back, and kind of this dawned on us that every down. The first big request that came along was the fact that even regular people were not had no access to masks. And I had just come back from a diving trip, and at that time I was just thinking about how can we contribute and help. And it occurred that we should evaluate snorkeling masks as PPEs. That led to a very large scale collaboration from 22 countries, the with the context of large scale medical companies like Boston Scientific and Medtronic. FDA was involved. And at this point, we have roughly released an equivalent of something like 45,000 of these snorkeling masks that have been adapted to be an equivalent to an N95 mask, except the big difference is that these are reusable and recyclable. So unlike a regular N95 mask that you just use once and then you're forced to dispose at the end of the day, we demonstrated, and I think there's a paper on PLOS ONE on all the work that we did, that we can use these for many months. We developed protocols for decontaminating them, and of course, partners with many manufacturing entities to make sure that we could truly build not just prototypes, but real products that are still being used. The last shipment for these went to Nepal for the last 1,000 masks that we have. And of course, when you look and do the numbers, because these things last months, this is roughly equivalent to roughly around 4 million N95 masks equivalents, because these filters that we are using are ventilator filters, and it allows us almost a week of usage just out of one single filter. Similarly, another project that got started, which I kind of call Project 1,000 by 1,000, that has taken a really unique turn. And I don't know if I have a picture for all of these projects have their own independent websites, so you can find out a lot more about it. I'll just mention a word of what did we learn in a year, but rather than, I won't spend too much time on the individual projects. So I mentioned new mask. The next one I want to mention is what we call this N95 factory in a box, which was an idea of could we truly manufacture N95 grade materials in the middle of. And of course, for some of you who have actually traveled around the world, you know that even a regular N95 is not available around. I mean, we spoke to many doctors in Bangladesh, for example, and one of the big lessons was they have never had N95 supply. So it's not the fact that N95 supply is in shortage, it's the fact that it's just have never been made available in the past. And we asked ourselves a question, could we reimagine in the future, not right now, but in the future, a distributed manufacturing facility for critical supplies? And that led to what we call a cotton candy machine turned into a filtration material. So this picture that you're looking at is a mechanism that we developed. This is all published now online, that allows us to make N95 filtration respirator filter material literally by modifying a 500 that anybody can buy on Amazon. And so for people who haven't eaten cotton candy, before, it's a fibrous material. And the idea was, could we actually use the same instruments rather than for spinning sugar, we actually spin elements of these polymeric meshes. At this point, that led to, once we published this, a partnership with a very large scale manufacturer, where they are now building what we call live manufacturing factory in a box, which is going to be the size of a shipping container, where we can go all the way from raw materials. And one of the key aspects of this project that we have demonstrated at this point in the lab is we could use recycled plastic. So you could say, take the jug of your milk jug, cut it up open, throw it in this system, and at the other end, get an object that has the capacity to really be able to make an N95, all integrated in a local manufacturing facility. And one thing that I'm very excited about, which has happened very recently, once we shared this idea with a broader community, several sets of communities reached out to us that have been building and designing menstrual pads, and especially hygiene products from a menstrual side of the story, where they brought up a challenge to us that, just like filtration, the active materials that are used in menstrual pads are not available around the world. So these are two manufacturers, one in Ethiopia and Uganda. And so now we are starting to think about a dual use of this manufacturing technology and deploy some of that in one in Ethiopia and the second in Uganda, to really test, could we actually build these super absorptive materials, which are the heart of many of these menstrual pads and many technologies related to that. So, there's accidental discoveries that happen along the way that I was really pleased about, because in the end, the idea of being able to be self-reliant in communities is extremely important. Along the way, I think there was a lot of work that we did on ventilators. Maybe I'll just highlight one project related to this, which is called Pufferfish. So you can go online and read about this. This happens to be a large-scale consortium with now 5 countries, 3 universities involved, where we have finally delivered a completely open source full feature ventilator. And as an example, this is, by the way, data to demonstrate that we can do an N95 grade material with the kind of a pressure drop that matches. And one of the power of this tool is that we can do programmable filtration materials. On the context of the ventilator, one of the design problems that we asked ourselves was, there was a lot of talk when the chatter started about the shortage of ventilators around these ambu bags and these temporary solutions. And one of the challenges that we saw was the fact that, why is there a fundamental shortage of ventilators? Because ventilator technology has been around for the last, almost 35 years. And that has been based around the know-how of manufacturing. There is nothing magical in building a full-featured ventilator, but there is no truly open source, fully featured ventilator. And the decision that we made was dependent on clinicians to make sure that we want to make a ventilator that clinicians will actually use, because there is a lot of know-how that's involved in building these. And I'm very happy to say that finally we actually have a product being released in India based on what we have developed. It's the first open source ventilator that will actually be manufactured in Africa. There is a manufacturing partner in Kenya that happens to be the Kenya motor manufacturers organization. So they are very good at manufacturing, but they had never thought before this to dive into the biomedical context, because they just didn't have the perspective for making medical products. And I think what we brought to the table with a very large team, this is not a singular effort. I built together a team with 3 universities, with many anesthesiologists out of University of Utah, many industrial partners. And at this point, what is remarkable about this is it has allowed and seeded essentially 2 biomedical companies, one in Kenya and one in India, for individuals that have manufacturing capabilities and quality control, but they would have never been able to dive in and think about that medical products is going to be a foray that we would go in. So it's been quite a remarkable journey and a learning experience. And you can check pestglobo.org to sort of follow through that project as well. I don't have a slide for it, but maybe I'll say a word about SnapDX. I know a few of you have volunteered for that as well. And I'm actually in the space where I do most of the clinical testing for this product. So I'll just briefly mention what this is and kind of give a quick demo and then dive into non-COVID projects. SnapDX came along with this context of truly tetherless molecular testing for COVID. One of the challenges, of course, that many of you have seen, and so I'll just go to this site so people could. So if you go to snapdx.org, you can actually see what we are doing and how it works. I'm not going to spend too much time on it, but I'll just mention what we are trying to do. Here is an object that is made with extrusion-based mechanisms. It's kind of like a Russian doll, and it's designed to really do a complete molecular assay. This is based on LAMP. But the key innovation that we have built in this situation is purely using hot water. So if you can make a cup of coffee, this comes in a cup, you can actually do this assay. So the way you begin is you open up this cap right here, you spit in it to a certain volume, you close it, you throw this in hot water that inactivates the virus, and there is a capture agent in the middle which moves from one chamber to the other chamber to the third chamber. And in the very last step, you essentially run what would be a classic LAMP assay, and a positive and a negative would look, I'm just picking up two of my samples to just show you. These are clinical, currently I'm in the lab because I'm running clinical validation assays. So you can see that right there. There is one is transparent and the other is pink. This one is actually a positive, that's a negative. And what's been project is this has really been built with volunteer help and support. At this point, we have done a user scale study of something like 700 people in the Bay Area to give us feedback on whether they can do this in their kitchen. Because the big portion of this study is, and again, there's a lot of politics around home tests, so I'm not going to get into that. We can talk for hours about it. And one of the key aspects of this is that the reagent cost for this around 50 cents, the plastic costs around 40 cents. So technically, if we get our chips right, we could deliver a $2 or a $3 COVID test, which has, I think from a context of sensitivity and the kinds of, we are collecting our clinical data, but you should think of this between 20 to 25 genomes per microliter is something fairly easy that we can actually detect.
And Manu, for reference, how does a standard PCR test compare on one side and like a antigen-based test like Binax now?
Yeah, so I think the way to think really about this is an amplification-based test. So much of the data that we already have from lab settings is something that you should really be thinking about. It still is an amplification-based assay, so it is not the classic antigen types of tests. But the key bit here is able to implement extraction in our process, but without electricity and without a framework of being in a lab. And currently, I'm collecting our sensitivity specificity data. The challenge that we have faced currently is access to positive saliva samples. At this point, I have 13 positive samples, and there's no point in reporting that it's 100%, but it's 13 positive samples. And I think this is something that I would love to talk a little bit about. We need positive saliva samples. I think we need to reach the number 30. In much of what has been demonstrated for LAMP, I'm actually pretty confident that we are going to hit the kind of marks that the FDA has put for a home test. There are several other competing technologies in this space from a LAMP perspective. What is unique about this by itself, it's extremely simple for us to manufacture. And it all uses is hot water. Unlike there is a lot of use and throw PCR machines that have come into the market. I mean, this is not about building $100 Apple Watch diagnostics world. That is good for certain framework of people. What I'm really excited about is using this as a framework to deliver molecular tests, and especially LAMP has been around. And really the Trojan horse of this, and I'll talk about this, COVID is good, but we're actually targeting this for TB. So a sputum test, we have one partner at this point to validate this in Peru, and another one in Guatemala, where we will do cohorts both for TB and for COVID. They've already started collecting samples. And I think because sputum is collecting early in the morning, it's actually quite valuable. There is not that much out there home testing for TB. That really is where my heart is. I think there is this set of scenario that even for the world, even 6 months from now, COVID testing needs to be much more broadly accessible. And on the science side, just for some people, maybe one thing that I can just mention, what is interesting about this technology per se is that there are no pumps and valves involved. We are just using thermodynamics to really do all the wash steps. So it's no different than if you actually do the centrifugation-based washing and extraction, and finally a reaction chamber, which is roughly around 20 microliters of a sample. But we've just been able to do it with just clever engineering. And if you go in here, you can see some of the details for how it actually works. I wish I'd put a slide for it, but oh, I don't think I have that slide. Okay, yeah, I think I can talk a little more about it if there are questions about how it actually works. One thing that I do want to mention is, of course, we ramped this up all inside the lab. And I remember, Andres is on the line, several other volunteers. I sent out this email to a lot of people. Hey, we're running this clinical study. Can anybody come? Just see the number of people that showed up. I mean, we have literally been assembling everything by hand along the way. So the sense of community that has been there in the perspective of COVID projects has just been remarkable. And I think what I'm really excited about is using this to really study a much broader group of tests. Okay, that's all I'll say about COVID. That was way too long as compared to what I wanted to say. Let's jump and briefly. And I want to then talk a little bit about malaria. So, this is I'm doing an abrupt switch, but I am aware of the time and this might. So, of course, this is a common quiz question I always ask. It's the wrong community to ask because you guys think about mosquitoes quite a lot. But, it's for a common average person, for the amount of impact that mosquitoes have on people around the world, the fact that we know very little about the ecology of mosquitoes is quite daunting. And one of the perspectives that we've been thinking about, what kind of surveillance tools that can be built for monitoring of viral load and viruses in mosquitoes in the field. And this has been a big challenge for us for the last almost 7-8 years. I've spoken to many of you about this project many, many times. I think I kind of call it the other than the ice bucket challenge, a mosquito bucket challenge, which is a common picture that you can see. This is a real postdoc in Australia who has a bucket of mosquitoes that has been given to him. And he has a little tweezer here. And his job is to count these. And I'm only making it a joke. I know this is a reality for many of you who work on mosquito biology. It's really hard to do ecology and surveillance at scale. So there are two things. Of course, there was an acoustic system that we developed called ABuzz. I'll briefly mention it, but I want to mention some updates on a new, it's not a new project, but we finally submitted this manuscript, which we call Vector Chip. This is two postdocs in my lab, Shelab and Felix. The idea was very simple. Yes, go ahead. Was there a question? Okay, I'll continue and I'll come back to it. The idea was very simple. Could we really build kind of a a fake human on a chip, or like a little card, something that looks like a business card that has tens of thousands of wells that we allow mosquitoes to bite. And we use those single bite to detect what was the viral load and what species of mosquito it was. So just like single cell sequencing has completely transformed science, we're interested in what could you do for single bites. And the idea is, so first of all, let's watch what happens when mosquitoes bite. You should think of mosquitoes as pipetters. So this is, to my knowledge, the first film that actually shows you the individual bites themselves. So we have stained our mosquitoes to be fluorescent by feeding them some fluorescent markers. And right there, I don't know if you could see where my mouse is, that little dot that appeared right there is another dot. These are individual bites, and the mosquitoes are leaving a tiny drop of saliva. This is between 4 to 6 nanoliters of saliva. But because this is designed in the context of a microfluidic chip, we can then process these bites and tell you exactly what was in it. So you can see the movie has started again. Those dots were not there. And when the mosquitoes are done, you're going to see a lot of these little individual dots. So what we do on the technical side is, so first of all, we built a lot of tracking software to confirm that individual mosquitoes were biting these wells. This is a single well, for example, and you can see this is where the mosquitoes explored. But to kind of jump directly to the actual results, what we were able to discover is something quite interesting, which is up till now, there are two materials that are often used when you do feeding assays. One is paraffin film, and the other one is the sausage skin, or this epithelial layer that's used. Both of those cannot be engineered. So we figured out a way to make PDMS films that are of programmable thickness. And by doing so, we can tune the thickness of this PDMS film such that one species of mosquitoes can bite through and others can't. So we can have a physical filter that we can build when we want to. So, these are the mosquitoes feeding on these. And you can see, for example, here in this data set, that there is a certain membrane thickness. And above that certain thickness, a certain species of mosquito will not be able to probe while the other one can. So we are using this to also understand mechanics of mosquito biting. But the result that kind of is relevant for many of you is this assay. So first of all, one of the assays that we did here with collaborators at Institut Pasteur is to have Aedes aegypti that were Zika infected. And we demonstrated a multiplex assay in individual bites to demonstrate that we can both detect Zika RNA, but we can also detect enough DNA from the mosquito itself. So we don't actually have to capture the mosquito. We can tell which mosquito did that bite come from. And what that leads us is a single multiplex assay that after a given number of bites, we can quantify very precisely how many of those mosquitoes possibly were infected. And the other thing that we did in this paper is a mathematical model that allows us to choose what should be the density of your bites that allows us to give a single bite per well. And that big experiment that you're interested in, we can tune that parameter and we can tune the size of this chip that allows us to count that. And then the last bit, which is also relevant, and I don't know if I have a picture for that, but it's in the paper. We have now also been able to demonstrate implementing the common plaque forming assays, the focusing assays, where we have a cell layer inside the chip. So we can confirm that active viral particle, and we can count individual viral particles based on the plaques that form on a cell layer. So we've been able to grow cell cultures inside our chip, feed them. This is only relevant for lab setting and not field settings. Feed them to a cage of mosquitoes that were infected, count the number of plaques, and use that to demonstrate how many. And as far as I know, this is the first time total number of active particles have been counted in a single bite. And what I'm interested in, I mean, all of that is just purely a demonstration. What we're interested in is now taking this tool for specific number of questions to really be able to understand them for, say both for malaria, but for also many other viral diseases. So this is vector chip. Much of this is online at this point, so some of you can read about it. And then since I only have a little time, I want to briefly update you all on what I've been doing with malaria. And so I'm going to just jump to that briefly. There's also another tool that we released recently called Bitoscope, which is focused on mosquito behavior, which is related to imaging. In the context of thinking about imaging, there is a large number of tools. There is the Plankton Planet that Brian had just described, which is much more focused around ecological measurements, but I'll just focus on Octupi. Octupi is our platform for automated malaria diagnostics. And then let me just mention to you, I mean, of course, you all know enough about malaria. I don't have to tell you. But let me just share with you an experience that I had in the field. So this is a picture from Kalahandi in Orissa. This is a site in India that has the highest density of falciparum. This is a tribal community. And the more I understood about the disease, I think the things that we learned along the way is that both the political situation has a significant impact. So it happens to be a Naxalite area, which makes it very complex for any government entities to really be able to provide the kind of services. And this is a life of a healthcare worker who works on malaria. This is going to be a time lapse, and you will see this health post from the beginning. So it's a single room hospital, essentially. She just walked in, and that was the hospital. And let me actually play this video like this. So it's just a quick time lapse. But for many of you who have done malaria microscopy, it's such a tedious task. And so this is Durga and Pranav, and they will stay there for 10 hours a day, and they will essentially image. And I know many of you who have worked in malaria know this firsthand. It's an incredibly difficult challenge to just really only do malaria microscopy. The kind of data that comes out of it is only yes and no. You might have some counts, but these smears are telling us a lot more. And then the other interesting thing here is that the dyes that are used, Gimsa, is this original paper from Mr. Juan G. Gimsa. That's from 1904. And it's been more than 100 years, and we are still using that exact same stain. I mean, it is a remarkable stain, but on the other hand, there is value in thinking about what could we do differently about malaria microscopy. That was our starting point. The tool that we built for it after many, many iterations is called Octupi. I think of this as a big brother of Foldscope. It roughly costs around $150 to build, but now it's a completely automated instrument. And then I'll just actually show you the data that I'm excited about. The purpose of this is it's completely modular. So head is for malaria, and then this other head is for TB. So we can swap these for different purposes. And I think what we are excited about is letting the community drive the research with these sets of tools. So let's just take a quick demo of how does this actually work. The object is roughly the size of my hands here. I've put the smear. At this point, the microscope is looking for its focus. It's finding its own focus. You can see the cell phone charger. The instrument will operate on this for around 8 hours. It's detected the focus, and at this point, it's just scanning. And now it's doing both fluorescence and bright field for every single image. So at this point, it started scanning. This is essentially, you can see at every spot it scans, it takes 2 pictures. And one of the kind of a quantitative number is we can image around 50 cells in around 3 minutes. So an average microscopist that sits roughly looks around between 3,000 to 5,000 cells with a 100x objective. And so the goal really here is to expand that by orders of magnitude, because these smears are telling us a lot. This is something that literally anybody who has some experience in robotics can actually build. We built this as an open source framework. There are lots of applications for it, diseases, but I just want to focus on malaria. There was an accidental discovery that we made in the context of this from a malaria perspective is, first of all, we can tune for the kind of questions we are interested in. So you can see that a $2 lens on octopi also gives us this data for we can detect the parasites, but we can also incorporate a $100 lens on that same, and you add capabilities and you can start getting images that are as good as, say, something like a $50,000 microscope in the lab. There is some amount of deployment that we have done already for this to learn from it, but I just want to show you the key data sets and the kind of discovery that we made accidentally. So this is a kind of data set that comes along, and what I want you to focus on the right is you notice this green pixel and a blue pixel. So I'll just focus in on this right here. This is the dye, it's just DAPI. But what you're seeing here is certain things look blue and certain things look green. We were quite puzzled by it, and we started thinking hard about it, and we realized that by making a low-cost tool, because we were not choosing our fluorescent filter sets to be very tight, we were actually doing spectroscopy. And what that led to the final answer of what we ended up developing, we discovered that we can essentially use the spectra of the emission from a DAPI to really be able to decipher platelets and parasites. And actually some of the staging of the parasites, and now we have done a lot of biochemistry to demonstrate it's a function of the DNA to RNA ratio in a cell is what gives this spectral shift, because it's staining both of these except the quantities are different, and hence we get this spectral shift. So you can see it's a significant of the peak is here versus here. And the best way to show this to all of you is in patient data. This is actually data from some slides that I've received from the UCSF group. And I'm just going to play this for a second. What you're watching on the left is automated data collected for literally millions of cells. This movie is 15 minutes long, and it is auto-registered. And you can see the top is octopi data and the Nighthawk, the more expensive microscope data. And every single time you see this blue, you see that's a platelet that's outside the red blood cell. While now this is the movie of millions of these cells, which are parasites. And every single time you see the green dot, you should actually be able to decipher the individual parasite inside the blood cell. So this is kind of the most fun movie I wanted to show you guys, because literally it's representing these 15 million cells, but it's registered to a $50,000 microscope and then a $100 microscope. And you can see we are not trying to resolve morphology. So we are using a trick that's used in astronomy. We're really trying to detect color as a way to measure to actually detect the parasite. So at this point, it's very robust, and we are ready to start testing this in the field. There's paper in starting to estimate. But one of the things that we are excited about is really turning microscopy from a data perspective to start looking like flow cytometers, because we have single cell resolution data. And of course, there is a lot more that we can do with these types of data. We have a complete blood count for the patient itself because we count all the other cells that are present. And then maybe I want to stop here, but I want to share a vision of what I've been thinking about this, which is there is a lot to be said with machine learning. But one of the challenges that I'm excited about is as we deploy the tools, we build the kind of infrastructure that enables and allows people to be able to build on our work, but also share capabilities with each other. So I know, for example, we have left one of these older version of Octopi in Uganda, but I don't know whether it's being used. And we also have one in Kalahandi. We are about to ship 100 more to many different sites. So what we are planning to do is with 15 institutes across Africa, Latin America, and India, is to build a network of a community which will help each other, train each other. Of course, the clinical questions every community will ask will be different, but there will be a cohort of people that will also share technical knowledge. And especially when one person finds a problem and one solves the problem, that can be shared dramatically with the community. So, and the hope really here is that we can have an open data sharing in this community such that we can really test this rigorously and simultaneously provide a lot of people who have been working on machine learning algorithms on these sets of data sets to really improve the firmware associated with this. So I'm actually quite excited about this idea. I've had a conversation with some of you in this network, but I am also hoping that some of you would bring all kinds of your networks along the way. And on that note, because it's already 3:03, I'm going to skip much of this and just thank the lab. All of this is not done alone. It's done in the context of a remarkable group of individuals that I get a chance to work with. So maybe I'll just go back to this cartoon here. Much of the work that I told you about for Octopi has been led by a remarkable graduate student, Hongchuan Lee. Much of the work on vector chip currently is being led by a postdoc, Shalab, with help from another postdoc who's now at Institute Pasteur, Felix. And SnapDX kind of has been my own passion with another research scientist, Anesta, and another postdoc, Adam, and just an army of volunteers from across campus. Pufferfish is really a large-scale collaboration between 3 universities, Brown, Stanford, and University of Utah, and partners across the world. And I don't know if I talked about any other project. Yes, the Cotton Candy Machine project was led by 2 graduate students in the lab, Pranav and Anton. Okay, on that note, I'll stop sharing so we can have some time for questions.
Thanks, Manu. That was fantastic. For anyone who, if you have to leave, that's fine. Anyone who has questions, hopefully Manu has a little bit of time to chat.
Yeah, I have around an hour. I basically blocked an hour. So I really would love to get some feedback because again, I really want to know how many of you think about deploying these kinds of tools because that we can't do alone. So anyway, I have time as long as